Hello, welcome. What do you call a lazy kangaroo? Obviously, a pouch potato. I kind of like that one. So today we are talking about exponentials. Okay, exponentials is another one of our nonlinear relationships, and it kind of looks like what I've drawn there. It gets larger and larger increasingly, or smaller and smaller increasingly. Let me quickly go through this. So essentially what gives a graph an equation shape or an exponential shape? What equation gives an exponential shape? Okay, whenever you have your variable as a power, and so normally it's x, sometimes it's t, but whenever your variable is a power, that's when you get this exponential graph. So for example, your most basic one will be y equals some sort of base to a power x. That would be an exponential. Even if I add a number at the front, and then I still have a power, that there is going to be an exponential still. And essentially, whenever you see your variable as your power, you're going to get an exponential type of graph. Okay, now it gets increasingly large or increasingly small very, very quickly. So if we're talking about money, money is one of those things that we want to grow exponentially. So when you invest with compound interest, eventually you do get some sort of compound graph, exponential graph. And it also has this thing called an asymptote. So I'm going to quickly talk about that there. So we do have an asymptote, and it's a line that the graph approaches, but it never reaches. Okay, so in this particular case here, is your asymptote is kind of right here. So you can see here how it gets closer and closer to zero, but it never really hits. Okay, so in this particular case, because that is a value of zero and all the horizontal lines would be denoted by y, would say here that your asymptote is y equals zero. That means these graphs get closer and closer to that 0 point, but they will never touch zero. It's kind of the same concept of if I keep, let's say if I start from 10 and I keep halving, I will never really reach zero. Okay, I wonder if that makes sense. So it's like 10, half that is 5, half that is 2.5, half that is 1.25, half that is 0.66125. I don't know what it is, but it keeps getting smaller and smaller, but you will never reach zero. That's kind of what an asymptote is. Okay. Now I've drawn this one here. Normally, if I have a what do you call it? If I have a base to a positive power of x, it's going to look this way. It's going to be what we call exponential growth, because as we're going from left to right, we're getting larger and larger, and that's what we call growth. This red line here, we're getting smaller and smaller. And so the way that this works here is there is a negative, but it's important to know where the negative is. So this particular one is your base is still a positive number. However, it is now your x that becomes negative. So just remember, whenever you get a positive x, generally, now not always, but generally, your graph will be growing and increasing. Okay. If you've got a negative x, what you'll notice here is your graph should get smaller and smaller. And there's a couple different cases for that, but usually that would be the case. Okay. Now, we're going to explore those cases a little bit, and we're going to sketch these using a table of values. We've got two different graphs. Now, they're both exponentials because I can see x is clearly my power. The only difference now is I have two different bases. My first base is 3. My second base is 1 on 3. Okay, when I say base, I'm talking about the number that the power belongs to. Okay, so let's do this. If you want to put it into your calculator, for this one, you'd go 3 to the power of negative 2, because that's what x is. And this case will give you 1 on 9. It'll be some sort of fraction. If I go 3 to the minus 1, that is 1 on 3. If I go 3 to the power of 0, that's going to be 1. And again, you can use your calculator for this. That would be 3 to the power of 1. That would be 3 to the power of 2. Okay. Now, if I do a third to the power of negative 2, what you'll notice here is when you put it in your calculator, you should get 9. And when you put a third to the power of negative 1, what you should notice is your answer is 3. This is going back to probably like year 10. I hope you remember anything to the power of zero. Any number to the power of zero should give you a number of one. Okay, and anything to the power of one is just itself. And this particular one, take a guess on what it is. It's 109. Okay, so I've done these in two different colors, so I can kind of show you. For 3 to the power of x, I can see this one here is 0. Oh, you know what? Let's do this. To make sure it all fits, I'm going to call this 2, 4, 6, 8, 10, because it does go up to 9. Now, I can see here that both of my y-intercepts should cut through 1. I don't know if you can see that. I hope you can. But what you'll notice here is they both go through that point. Okay, so if we're talking about a simultaneous solution, there's your simultaneous solution. But without further ado, let's actually sketch in these points. I'm going to call this -1, -2. So I'm going to use a slightly different scale just so it's not too bunched up. Okay, at -2, it is 1 on 9. So it's still positive, but it's really tiny. At -1/3, at -1, it's like a third. So it's still positive, but definitely really tiny. At 0, it's 1. At 1, it's 3. And at 2, it's 9. And so you can see here, it grows quite quickly. And I'm going to try my best. It's not going to be perfect, but I want you to imagine that it is. Okay. So that there is my y equals 3 to the x. And if I was to sketch the blue one, what you'll notice is it actually goes in the exact opposite direction. So when x equals to -2, y equals to 9. So I'm going to kind of match that up there. That's about here. And when x equals to -1, it equals to 3. So that would be roughly about there. And then when it was 0, it was 1. So it goes through that same point as the other one. And then it gets smaller and smaller. At 1, it's a third. So just pretend that's a third and pretend that's 1 on 9. And you can see here that this graph does something similar. It just goes the opposite way. And we draw arrows on both sides to show that these will kind of go on forever and ever. It'll get closer and closer to 0, but it will actually never reach 0. Okay, so if you keep punching numbers in your calculator, your numbers will get closer and closer to the number 0, but they'll never hit it. Okay, until your calculator runs out of decimal places. So a couple things to note, and I'll write a little note here. If the base is larger than 1, your exponential should go this way. Okay, if the base is smaller than 1, that means you'll end up going this way. Okay. Now, of course, when you start coupling in your powers, that starts to change things. But just in general, this is what I would recommend. If your if your base number is greater than 1, so 1.2, 2, 7, 12, 150, any number that's bigger than 1, your graph is going to go larger and larger and larger. If your number is in between 0 and 1, so it could be a half, a third, a quarter, 0.95, anything less than 1, you'll find that your kind of your graph becomes smaller and smaller. Okay. I hope that helps, and I will catch you guys in the next one. See you later. Bye.